Okay, so today we're still talking about um, fundamental theorem. Fundamental theorem means two things: antiderivative, find the antiderivative, and then evaluate, right, to find area under the curve. We're still doing that. Nothing's changed, but we have a new type of function, inverse trig. Inverse trig. We've had inverse trig last semester too. But now we have for integration. Okay, so on your sheets with your derivatives and integration sheet, I think yours is pink. I think it's on the other side of the unit circle. The derivatives of an integral side. These are from there. Okay. So last semester we did antiderivatives, or not derivatives of things like inverse sine, inverse cosine, inverse tangent, inverse cosecant, inverse secant, inverse cotangent, right? This semester, since we're doing integration, antiderivatives, we only have three. There's only three, okay? And those are down here. Those are at the very bottom. Those are the last 16, 17, and 18 on your sheet. The very last ones. Those are the ones that I have up here. Okay, there's not as many for integration. There's only three. But again, just like derivatives, it's just something you got to kind of notice, see, recognize, right? If you notice these relationships here, one on top, right? Du just means there's a one on top. There's nothing on top. And on bottom, we have a squared. We have u. A is a number. U is the variable. Okay. So if you notice one of these relationships, the derivative or the antiderivative will be either arcsine, arctangent, or arcsecant. So remind me, what does inverse trig mean? When I say inverse trig, what does that mean? What are we doing? Why do we use inverse trig? Why is it sometimes needed? Inverse trig. Like when we use trig, we use it to find things like sine, cosine, tangent, things like that. What's the difference between that and inverse trig? But what does that mean, though? What does that mean to find arcsine, arctangent? What do those things mean? Like if I'm finding sine of something, so let me write this down. You don't have to write this down. I'm just gonna. So if I'm finding sine of pi over 2, right? That's trig, right? You go look at the unit circle, and it's y over 1, right? When do we use arcsine? Or inverse sine. Inverse sine and arcsine are the same thing. Sometimes it's written like that. Sometimes it's written like this. It means the same thing. When do we use those? Sure.
When they are in the denominator, or like it's 1 upon sine x, so it would be like in the denominator.
So when we have the answer, when I have the answer. So if I know the answer, if I know this part, but I don't know this part, that's when I use arcsine. Okay? So if I don't have the angle, I need to use arcsine. If I have the angle and I need to find the proportion, then I would use regular sine. Okay? So for example, arcsine, I would use if I'm saying or right? That's what I would use to find arcsine. Where is this the answer? That's what I'm asking. For these guys, I'm asking, where is this the answer? Where is this the answer? Where on the unit circle is that an answer, right? It's just the inverse. I'm asking the opposite question. Instead of saying, go to this angle, what is sine at that angle, right? I'm saying, here's the answer. Where is that the answer, though? Where is that the answer? It's flipping the question. That's all it is. That's why we use inverse sine, inverse cosine, inverse. That's why we use those. When we know the answer, we just have to find the question. Okay? Okay, so let's look at letter A. So there's really no trick to doing these. I don't spend a lot of time on these because there's not a lot of math. It's just you have it's something you have to recognize. Like if you see this guy here, right? If you see this guy here, it's just usually there's going to be a square root at the bottom. For two of these, there's a square root at the bottom, right? And then it's a squared minus x squared, or whatever the variable is, right? So this guy here matches this guy right here, right? But the 2 is not there. What do I do with the 2? Not factor it out. Move it to the front. Move it to the front, yeah. Mm-hmm. So now it becomes, I can put the dx up here. Okay. So then I go look up here and I see, oh, it looks like arcsine, right? A is 1, u is x. I can rewrite it like this. Okay. So the antiderivative is going to be arcsine or inverse sine u over a. Well, u is x, a is 1. I don't need a plus c on this one because this one's got bounds. So I'm actually going to evaluate it. All right. So I need to plug in arc sine of 1 minus arc sine of 1/2. Okay, so it's asking where on the unit circle am I going to get sine of 1? Where on the unit circle am I going to get sine of 1/2? So you got the unit circle, take a look. There's a couple spots where you're going to have where is it? This is from your notes. The only spot that we want for arc sine, give me all of the angles from negative pi over 2 to positive pi over 2. Okay, that's what I want to write down. All of the angles from negative pi over 2 to positive pi over 2. Well, 1. Sine of 1, I have positive pi over 2, right? That's the only spot I have 1. So pi over 2. minus 1/2. 1/2, I have it at pi over 6. 5 pi over 6. I have it at pi over 6 and 5 pi over 6. Well, again, I only care about these values here, right? So I'm only going to use the pi over 6. Pi over 6. Subtract those two. 3 pi over 6 minus pi over 6 equals 2 pi over 6, which equals pi over 3. Mm-hmm.
Were we supposed to multiply we moved the 2 to the front of the end?
Oh, sorry, yeah, we still have the 2. Mm-hmm. So you're going to multiply your answer by 2. We still have the 2. Yeah, I forgot to write the 2 in. So the 2 is right here. So whatever answer you get, you just multiply it times 2. So it's going to be 2 pi over 3. Yeah, thank you. That's very important. Okay. All right. So let's look at letter B now. So letter B, looks like letter B doesn't have a square root on the bottom. Looks like it matches arctangent. Looks like it matches arctangent. So I can rewrite it as okay. So its antiderivative is going to be 1 over a. Well, a is 1. Arctangent u over a, x over 1. And I have to evaluate that. Running out of room. From root 3 to negative 1. Okay. So that means I'm going to arctan of root 3 minus arctan of negative 1. So when I'm finding arctangent, I only want from negative pi over 2 to positive pi over 2. From negative pi over 2 to positive pi over 2. Those are the only values I'm looking at when I go to my unit circle. Okay. So we need pi over 3. Got one here. Got one here. Well, the only ones I want, I can't go over pi over 2. So I don't want this guy. The only guy I want is pi over 3. So pi over 3 minus arctan of negative 1. Arctan of negative 1. Let's see, I got one here. I got one here. Which one of those am I going to use? Yeah, the bottom one, right? I'm not going to use this guy because this guy's too big. This guy goes over pi over 2. But doesn't this guy down here do that too? Doesn't this guy go over pi over 2? But why is it okay to use that?
Because that's also negative pi over 4.
Exactly, because it's also negative pi over 4, right? Right? If I go the opposite direction, this is negative pi over 6, negative pi over 4, negative pi over 3, negative pi over 2. Okay, if I go the opposite direction, if I go this way, it's as stated. If I go this way, negative pi over 6, negative pi over 4, negative pi over 3, negative pi over 2, and so on and so forth. Okay? So this is the guy I want right here. That is negative pi over 4. Okay? Minus a negative. Common denominator. So the common denominator for pi, for both of them is going to be 12. So that's going to be 4 pi over 12 plus 3 pi over 12 for this guy. So you get 7 pi over 12. Okay. Okay, so I want you to do letter C and letter D. Letter D, you don't have to do the evaluation part. There's no bounds. It's just indefinite. C, you have to. Okay, so I want you to do C and D. Okay, so the first one is arctangent again. I had to move around the x and the 1. It's okay, it's addition. You can flip-flop them. Order doesn't matter when you're just adding the denominator here. So arctangent 1 to 0. Arctangent of 1 is pi over 4. Arctangent of 0 is 0. You get 5 pi over 4. The other guy, it's not bounds. There's no bounds. There's no bounds. So we just have to, we're going to use a plus c on this one. Okay, so this one is the one we haven't used, which is arcsecant. Okay, so arcsecant. So anywhere there's an a, I'm going to put a 2. Anywhere there's a x, I'm going to put, or u, I'm going to put an x. And then I have a negative 1 in front, though. So it's 1 over a, 1 over 2, arcsecant, and then the absolute value of x over 2 plus c. And then you multiply, you get negative 1/2 arcsecant, absolute value x over 2 plus c. We don't have to evaluate anything because there's no bounds. We're done. Okay, there's not a lot of those. Like if you take an entire practice test, you might have one question like that. If you take an entire one of our tests, you might have one multiple choice question like that. But they're questions that are important because every point counts. Like on our tests, the difference between getting, the difference between getting one of these right on a multiple choice and not getting it right could be the difference between an A and a B. Okay, so are they important? Yeah, they are important. Are they as important as other things? No. But like I said, it could be the difference if you're taking the test between an A and a B in this class. Okay, on that test. So you always want to make sure that you have those, and there's only 3 of them. There's only 3 of them. Mm-hmm. Yeah.
You know how we have done like several problems yesterday?
Yeah.
They had some like this, so we took like the negative power of them and did it.
If they fit this, then you could use it. So if they fit one of these guys here, you absolutely could use it. Yeah.
So like they would still have different answers if we used
I have to take a look at them. I'll take a look at the questions because I think I know which questions you're referring to. But yeah, I'll take a look at them. But yeah, if they look like this, is that the only way to solve them? No. but they should have the same answer. Yeah, so I have to do some more investigating on that, yeah. Okay. Okay, so last thing, average value. Average value. Also known as the mean value theorem of integrals. We had a mean value theorem last semester. Mean value theorem last semester dealt with comparing the instantaneous derivative, the derivative of one point versus the derivative over an interval, right? Let's see. The mean value theorem I might have a picture here. The mean value theorem for derivatives said the derivative, so if my interval is from here to here, the derivative from there to there, which is the slope, somewhere in between there, it has to have the same derivative. So somewhere in between these two dots has to have the same derivative as the average derivative. Okay, that was the mean value theorem for derivatives. Now we're coming back to that, but this is a little bit different. This one deals with area. Mean value theorem for derivatives dealt with slopes. Mean value theorem for integrals deals with area because integrals is area. Okay, so this is the formula. This is the formula. But I'm going to explain what it is. What is average value formula, mean value theorem? Well, this is what it is explained. Okay, so I drew a little picture here. Okay, so if I have a function from A to B, right? If I have a function from A to B, that's the function there. And I were to find area under that curve, that's the green. What the average value formula or the mean value theorem of integrals tells you is where on the y-axis am I going to create a box, a rectangle that has the exact same area as the green stuff. Okay, so the green stuff is this. It's kind of, you can't really see the green because it's, so all of this green is the area under the curve. All of the green is the area under the curve, right? Which we've been doing. Now, what the average value formula or the mean value theorem is going to do is going to say, okay, how tall does a rectangle need to be? How tall does a rectangle need to be? Where is the height of the rectangle? That if I were to make this rectangle here, it would have the same area as the green stuff. This box and the green are exactly the same area. That's where it tells you. It tells you that value, that number, C. So it gives you the height. Where would the height be? Okay, where are they equal to each other? And this is the formula there. The value, that y value, that height, is equal to 1 over b minus a times the antiderivative from b to a. Okay? The formula is the formula, but it's good to know why we use the formula, where the formula comes from. This is the average part here, right? If I was to find average of 21 plus 14 plus 13, if I was to find the average of those three numbers, I would add it up and do what? Not by 3, right? In other words, take a third of it, right? That's exactly what we're doing over here. That's where that fraction comes in here, right? So I'm only taking a piece of this guy here. That's what I do with averages, right? I just take a piece of the whole, right? I just take a third of the whole, right? It's the same thing. It's just the same thing, but dealing with the area. Okay? Okay, so that's essentially what we're doing. All right, so let's look at example number 2. Okay, so example number 2. The function that creates the area under the curve is this guy right here. That's the function. What is the average value of f on the interval from -1 to +1? Okay. Now, I'm going to draw a picture that's not to scale. This is not to scale. Okay. But I just want to kind of give you an idea of what we're doing here. So from -1 to +1. Right? This is not to scale. So don't think that this is exactly what the function looks like, but I'm just going to draw this picture. Right? I can find area under the curve. Right? I can find the height of the green stuff. Or the area of the green stuff, right? I can do that. That's what we've been doing. Fundamental, that's what the fundamental theorem of calculus tells us, right? Here's the thing. What the average value will do is it'll give me a height of a rectangle that will have the same exact area as the green. So it gives me a rectangle that will have the same exact area as the green. That's what I'm trying to do. Okay? So how do I do that? This is what I do. Where is the area under the curve? Well, how do we find area under the curve? How do we do that part? By integration, right? By figuring out antiderivative, plugging in numbers, get a number like you guys just did on the assignment yesterday, right? That's what you guys were doing. So I need to do that, and I need to figure out where is that rectangle going to be equal. But I know the width. The width of the rectangle is going to be the same, but I need to find the height of the rectangle, and that's what it helps me do. Okay? So I'm going to use this formula here. F of C is my answer. Okay, so 1 over B minus A. What is B and A? B is the top bound, A is the bottom bound. Okay. So what is the top bound going to be? 1. What is the bottom bound? -1. Next, we write the function. -x squared minus 4x dx. Okay? That's what we were doing yesterday. Average value says, okay, now you need to take the average of it. Well, the average of it is a fraction. B minus A. Well, we said that B was 1 minus A is -1. Right? So in other words, 1 plus 1, 1/2. And then you just finish the rest. 1/2 antiderivative. So I get negative x to the third divided by 3 minus 4x squared divided by 2. And I have to evaluate that from 1 to -1. Just use the power rule. That's all I did. I just used the power rule, which we've used many, many times. I didn't have to use U substitution or anything. Okay? So 1/2 -1/3 x to the third power minus 2 x squared minus -1/3 x to the third power minus 2 x squared. I'm going to plug in a 1 over here, and I'm going to plug in a -1 over here. Whatever answer I get, I'm just going to multiply times 1/2. And that'll be the average value. So let's see, I get -1/3 minus 2. And then I get +1/3 minus 2. So I get -2 1/3 minus 1 2/3, or minus -1 2/3. Probably easier to change them. So I get 1/2 -7/3 plus 5/3. 1/2 times -2/3. And I get -1/3. Okay, that's how tall. Doesn't need to be very tall. Doesn't need to be very tall. Probably because, like I said, my picture, this guy probably should have been down here. Okay. All right. Okay, so next one. Average value. Here's the function. Here's the interval. Go for it.
What was the answer for example number 2 again?
All right, so sine of pi over 3x. So I had to use sine of pi over 3, or pi over 3x, I should say. That was my u. And then 1 minus 9 over 2 minus 1/2 is 1/4, because it's 8 over 2, which is 4, so 1/4. Excuse me, found antiderivative. Got -3√3 over 8 pi. Okay. All right, one more. We're going to do practice with this tomorrow. I'm going to give you some more problems to do tomorrow. But for today, I just want to kind of get some practice, see what we're doing. And then tomorrow, I'll give you some time to do some more practice. We're not going to do a new lesson tomorrow. Okay, one more. Average value. So we have an f of x, and we have from 1 to 4. Write your answer as a logarithm. So they're telling us right now we're going to get a log answer. Okay? So we should have a log or ln answer. All right? Well, set it up. We see average value. So anytime you see average value, it's going to be the same setup. It's going to be f of x and then 1 minus 4 minus 1, which is 3, 1/3. So I have 1/3, 4, 1. You can change x minus 7 to -1 power, but automatically, if you have something up here that doesn't have an x and something down here that does, you're going to have to be using, it's a grouping symbol. It's already grouped together. Division is a grouping symbol. So I'm going to have to use some u substitution. Okay. So I get 1/3 from 4 to 1, 6 over u du. What do I do with the 6? Move it to the front. Okay, it becomes a 3. 1 over u, or u to the -1. Anytime you see this, it's always going to be, the antiderivative is going to be natural log. Natural log, so that's where the log comes from. So you have a 3 in front, and you have natural log of u, 4 to 1. 2, where? 2, 2, 2, 2, 2, 2, 2, 2. Oh, yeah, wait. Yeah, you're right. I did not reduce correctly. Yep, that's going to be a 2. Thank you. Okay. All right. 2 times. And then I'm going to plug in back u, x minus 7 minus x minus 7. So I'm going to plug in a 4, and I'm going to plug in a 1. I can't have negative natural logs. So whatever my answer is, it's got to be positive. So you're going to have 2 times the natural log of 3 minus the natural log of 6. Since I can't use a calculator, it says write your answer as, oh, I know what I wanted. I know what they got to do. So what they're going to do here is use some of the powers. So remember, if you have a number in front, you can use this. So they're going to want you to use some of, not the powers, the properties. So they're going to want you to do, move that guy to 1 log, 3 over 6, which is 1/2. And then this guy here is actually a power. It's the log properties you guys did in Math 3. We haven't used them in a while. But yeah, there's 3 log properties: the power property, quotient rule, quotient property, and product property. Okay. So tomorrow I'm going to give you an assignment, just like I did yesterday. I'm going to let you guys work on that. That's all we're going to do. And next week we'll finish up the chapter. All right.